Now that I've terrified you, let's start. What is the law of conservation of energy? Well, I'll give you the sciencey definition. It says this. The total energy of a closed system is neither increased nor decreased by any process. Energy can be transformed from one form to another, but the total remains constant. You want the short version? Energy's got to come from somewhere. And it's got to go somewhere. Energy doesn't vanish. The more poetic version says this: the amount of total energy in the universe is always constant. In other words, the amount of energy that occurred after the Big Bang, that's what we're stuck with. That's all we have to play with, and that will never change. We can transfer energy from one thing to another, but we can't manufacture it from scratch. As an equation, we say this. KE initial plus PE initial equals KE final plus PE final. The amount of energy you had before has to equal the amount of energy you had after. Or, if we include friction, and now we kind of can be a little more accurate, KE initial plus PE initial equals KE final plus PE final. If the numbers don't balance, then Tyler will assume whatever's missing went into heat. Went into heat. I wrote here, Mr. Dewick has a good demo for this. You've seen it behind me on the board all year long, and you've wondered. So the beautiful thing about the law of conservation of energy is, because energy is a scalar, I can use it to analyze or to deal with yucky, curvy paths. I notice it's saying not responding. I'm really hoping that it will open it properly, Mr. Dewick. Come on. Oh, it will. Okay, it's working. Skate ramp. Skateboarder. Okay. If I put him up here, what type of energy have I given him? Potential. When I let him go, what will it turn into? Okay. Now, I have no friction, so we're in our magic physics world, but I want you to notice the total energy stays constant. At the very, very top, it's all potential, which means kinetic is getting smaller and smaller. Kinetic energy is a half mv squared. Is his mass getting smaller? No. So what's getting smaller? Oh, speed. That's why he comes to a stop at the top. And then, as his potential energy lowers, what happens to the kinetic energy? Gets bigger. Does his mass get bigger? No. His speed does. That's why you speed up when you go down a hill. Total energy stays the same. Okay? Now, what I don't have in here is friction. So let's bring in... Oh, by the way, the other great thing about this is because energy is a scalar, it really doesn't care about the path that you took to get there. So I can even add a little bump, smooth it out. Okay. Now, I'm going to have to make the skateboarder get glued to the track, because otherwise in real life he might fly off and get air, and that totally changes the question. So we're again in our magic physics world. I'm going to turn friction off. I'll put the pie chart and the bar graph on. So here's his energy. Again, the total energy doesn't change. And so if you give me a yucky, curvy path, Jake, a roller coaster, the best way to analyze it is going to be with the law of conservation of energy. Let's bring in friction. Let's add just a little bit of friction. There. Now you'll notice that the thermal energy, the heat energy, is going up. Is the total energy changing? But because you're bleeding away some energy to heat, you're ending up with less and less left over for potential and kinetic. In fact, he may end up either at the bottom of this. Okay. And he'll eventually come to a stop. Now, The ground level isn't here, so his potential energy won't be 0. But one of the really nice things about this also, Tice, is I can put the ground wherever I want to. Usually I'll just put the ground at the bottom of whatever I'm looking at. Even if what I'm looking at is hanging in the air, I'll just say, I'll put the ground there. That'll be 0. This is the law of conservation of energy. Let's do a simpler one with friction. Let's turn in the bar graph. So we'll give them all the potential energy. This is what really happens if any of you skateboard. You're losing much of your energy, partly to friction, but also because you're bumping into air molecules. Each of those air molecules is taking some kinetic energy from you. Air resistance plays a pretty big role, it turns out. But are you losing the total amount of energy? Nope. It's not being created. It's not being destroyed. It's constant. So, example 1. A projectile. We could solve this using projectiles, but I want to show you that we can also solve this using conservation of energy. Is launched straight up into the air. If it reaches a final height of 93 meters, what was its initial velocity? Use energy to solve this. I could solve this by making a T-table, by putting an H for horizontal, a V for vertical. You know what? I said use energy. Oh, here's my question. In the last unit, it was a free body diagram, the obvious one. Here's my question here. Is there a change in height in this question? Is there a change in speed in this question? This is a job for conservation of energy. This is going to be my trigger phrase here. So I'm going to go like this. KE initial plus PE initial equals KE final plus PE final. I'm going to ignore heat. How do you know? Because they didn't say include heat, honestly. Kinetic energy. What was the equation for kinetic energy? A half something. Okay, so this is going to be a half mv initial squared plus mgh initial, potential energy was mgh, equals a half mv final squared plus mgh final. Are any of these 0? Oh, well, first of all, is there an M in everything? Yay. Is my initial speed 0? No, because that's what they want me to find. Is my initial height 0? Are we starting on the ground? That whole term goes. What about at the top? How fast am I traveling at the top? That whole term goes. What about at the top? Is my height 0? No. So now I get this. 1/2 VI squared equals GH. What am I trying to find here? How would I get it by itself? What do I do with that 1/2? So this is the same as putting a 2 right there. And then how to get rid of a squared. So if I hear you correctly, my initial velocity is going to be 2 times 9.8. Mr. Duke, why not negative 9.8? Working energy or scalars. Okay. Times the height, 93. $42.7. Meters per second. I could have solved that using projectiles. In fact, I'll be honest, Addie, I probably would have solved that by saying VI equals question mark, VF equals 0, A equals negative 9.8, D equals 93. I think I could have used VF squared equals VI squared plus 2. I could have made it work. I would not be able to do that for example 2. A 350 kilogram roller coaster car, I love roller coasters, is traveling at 22 meters per second. If the car starts out at a height of 12 meters, How fast will the car be traveling when it gets to ground level? So I guess we're talking about some kind of like that. Don't write that down. Is there a change in height? Yeah. Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy because it's a scalar. That's really going to be my fallback every time, Jose. Is there a change in height? Is there a change in speed? Especially if there's a yucky, curvy path. Really, I can only solve it with conservation of energy, a scalar approach. To solve it with a vector approach, Rob, I'd be doing components left, right, and every time we weren't dead level or dead vertical or dead horizontal, I'd have to break out the components. Oh, wait a minute, it's curving. The angle is changing all the forget it. Let's go to a scalar approach, please. Which means kinetic initial plus potential initial equals kinetic final plus potential final. The amount of energy before equals the amount of energy afterwards. Pause for a second. Come. Ready? Are any of these zero? You know what? I'm an adult. Here's my roller coaster. Whee! So we're starting here. We're ending here. Is that okay, Rob? Now here's the beauty. Work and energy is a scalar. They didn't need to tell me what the roller coaster looked like because work and energy doesn't care, don't write this down, if the roller coaster dropped really fast and ended up on ground level. In fact, it doesn't even care if the roller coaster went down into the ground for a while and then popped up here. All work and energy cares about is where you start and where you end. It does not care about the path in between, which is nice. Are any of these zero? Am I at rest right here? Read the question carefully. No, see, got to read the question, right, Ty? So am I at rest right there? No. Am I on the ground right there? That's meant to be Captain Obvious. The answer is no. Am I at rest here? I don't think so. That's what they want me to find. Am I on the ground here? So which of these can I cross out? You'll notice this time I crossed out one line earlier instead of writing in the equations. You can write in the equations and look at the V and the H, but it's either going to be a V or an H. Sometimes they'll be zero. Not always, but sometimes. So I'm going to get this. A half mv initial squared plus mgh initial, a half mv final squared. What? Tice, have you been on a roller coaster before? Yeah. When you got on the roller coaster, did they make you step on a scale before you got on the roller coaster? Did they have to balance out all the masses? Did they have to make sure that a fat person sat next to a skinny person? Do you know why? More specific, the two words that you said earlier. Masses in this equation cancel. I don't know if you ever wondered why or I'll give you the other really obvious one. Can an empty roller coaster make it through the track the same way a full roller coaster can? Yes. Why? Two words. Masses cancel. Okay. So, I don't know if you ever wondered why you don't have to step on a scale before you get on a roller coaster, but you don't. What am I trying to find here? What am I trying to find here? V final. I'm going to show you what's right in front of the V final. What fraction is sitting there? Here's what I'm going to do. Because there's also halves elsewhere, I could divide by 0.5. I'm going to give you a great trick. I'm going to clear the fractions. I'm going to go like this. Times by 2, times by 2, times by 2. Is that legal? Did I multiply everything by 2? So it is legal. Why did I do that? Because what's a half times 2? What's a half times 2? And I get this. Vi squared plus 2ghi equals Vf squared. Put your pencils down, look up. You may recall near the beginning of the year, I told you that someday I would prove to you where this equation came from. I said to you, The proof is kind of complicated right now, but when we get to conservation of energy, VF squared equals VI squared plus 2AD will just plop right out. See it? Because G is A, yes? And H is D, yes? There's the equation. Really, you can derive it in 1 second from the law of conservation of energy. That is VF squared equals VI squared plus 2AD in disguise. So I kept my promise. I told you I'd show you. There it is. What are we trying to find? Pick your pencils up. Oh. Square root. Okay. So VF is going to be 22 squared plus 2 times 9.8, not negative 9.8, conservation of energy, work energy, scalar, 12. I think I'm going to do everything in the square root, hit equals, and then go square root answer button. Oh, first of all, when he gets to the bottom of the hill, should he be going faster or slower? So if you get an answer less than 22, you've screwed up. There's a built-in error check, right? We know some physics. So 26.8. That's not much faster, Mr. Dewick. 12 meters is not a very big hill. Roller coasters are much higher than that.
Meters per second.
Oh, meters per second. Thank you. I want to hand it. Yeah, you'll get one because you caught me on something else earlier too. Remind me, make sure I give you your candy. Example 3. Example 3. Lewis, what's example 3 asking me to find? Heat energy. Is there a change in height? Is there a change in speed? Yeah. Is there a yucky, curvy path? Not really. Are they talking about heat energy? You know what? This is a job for conservation of energy. But this time they mentioned heat, so I'm going to modify my equation, Lewis. It's going to be this. Kinetic initial plus potential initial equals kinetic final plus potential final. But this time they wanted, you know what? They're saying you lost some to heat. I put it on the right-hand side because it's part of the afterwards. Some of the energy went into heat, apparently. Are any of these zeros? Are we ending up on the ground? Tyler, I think you were right as well. What does dropped mean? What's VI if I drop something? What's VI if I drop something? Now, I heard somebody say, isn't the final velocity 0? No, that's after it hits the ground, Captain Obvious. I assure you, the final velocity when it hits the ground isn't 0. Otherwise, I wouldn't have needed a parachute when I jumped out of an airplane. I mentioned I jumped out of an airplane. I wouldn't have needed a parachute. So please get out of the habit of saying when something hits the ground, that means VF is 0. That's V after everything is done is 0. But VF, I assure you, is not 0. What am I trying to find? Lewis? How would I get the heat by itself? Okay. So I'm going to get this. I'll write the heat first. Heat equals, and I guess it's potential initial minus kinetic final. Heat equals mgh initial minus a half mv final squared. Does the mass cancel this time? Tyler shook his head. Tyler is correct. Why not? Because there isn't an m in everything. There's no m in heat. If there was somehow an m in the heat expression, then yes. But nope. What is the mass? And you know what? That makes sense. I have a feeling a bigger object would generate more heat. Anyways, 18, yes? 9.8, 40, minus 0.5, 18, 25 squared. 18 times 9.8 times 40 minus 0.5 times 18 times 25 squared. Apparently 1,431 joules, I'll call it 1430 to 3 sig figs, joules of heat were generated. Is that right? Anyone else get that? Yep. You know what? It's heat. I'll do that in red because that seems like a heaty color. What did I say? 1,430 joules. Example 4. A couple more, right? See how far we'll get. Example 4. How much work is needed to slow down a vehicle from 80 kilometers to 50 kilometers? Okay, this question is not saying find a speed or find a height. This is asking, well, what's this question asking me to find? How much what? Work? Work equals force times, wait a minute. Is there a force mentioned anywhere in this question? Do you see newtons anywhere in this question? Do you see a distance anywhere in this question? I'm not going to use that definition of work. Work is also the area under a force versus distance graph. Oh, wait a minute. Did the question give me a graph? Well, I'm not going to use that. Here's our third definition of work, the work energy theorem. It equals the change in potential plus the change in kinetic. We're talking about a car, a vehicle. Does this question mention a hill in the question anywhere? So I'm going to ask the same question. Tyler, I'm just going to phrase it differently. Does this question suggest that there's a change in the height in this question anywhere? I'm going to ask the same question. I'm just going to phrase it differently. What's the change in potential energy then? 0. I can ignore it. But what's change in anything? Final minus initial. So I guess the amount of work is going to be a half mv final squared minus a half mv initial squared. 0.5. Oh, does the mass cancel here? There's no m in w, or in other words, it does take more work to stop a bigger car, which makes sense. 1,200. What's v final? What's v final? 50. 50 what? How do I go from kilometers per hour to meters per second? It was something with a 3.6. You know what? Let's go like this. 50 over 3.6 all squared. Why don't I just, if I'm going to divide by 3.6, why don't I just do that right in the equation? Isn't that clever? Minus a half times 1,200. What's v initial? 80 divided by 3.6 squared. Oh. Let's try that. Half times 1,200 times 50 divided by 3.6 squared minus a half times 1,200 times 80 divided by 3.6 all squared. Is this car slowing down or speeding up? I'm going to ask you the same question. I'm just going to phrase it differently. Is this car gaining energy or losing energy? It's losing energy. Am I expecting negative work or positive work? Negative work. It lost 180,000 joules, 181,000 joules of energy. Is that right? Same answer as me? Anyone else? Yep. Work equals negative 181,000 joules. So there's the answer to the first question. Then it asks, what force does the work? Which force is it that makes a car slow down, or speed up for that matter? So where do you think all that extra energy, that negative 181,000 joules of energy, got transferred to? Heat. And that, my friends, is why brakes can overheat. Now, I took a Tesla for a test drive this summer. The Teslas are very cool. They actually, instead of bleeding that energy off into heat, they actually bleed that energy off into recharging the battery. The car still slows down because you're pulling kinetic energy out of it, but you're not overheating. In fact, you're not even using the brakes. You're not overheating the brakes. You're not using the brakes. They actually told me they advise owners of the Teslas to get their brakes checked every 10 years or so because you barely ever use them. The car just slows down because you're recharging the battery. The energy, it's electrical energy, which we'll talk about later this year, but where does the energy come from? It's got to come from somewhere. It comes from the car's kinetic. Example 5. A 12.5 kilogram object is pushed across the level floor with a mu of 0.35 for a distance of 6.4 meters by an applied force of 58. You know what? I better dope. Here's an object. It looks like I have an applied force of 58 newtons. And it says there is a mu of 0.35. Okay. Isaac, what's A want me to find? Done by what? Okay, so my first, when they say how much work, I always start with, well, maybe I can go force times distance. I start there. Oh, which force did you say? So I'll even say, and then I would say, did they give me the applied force? They did. Did they tell me the distance the applied force was acting? They did. And I need to ask one more thing. Is the applied force and the distance, are they in the same direction? Then this will work. No pun intended. I think I can just go 58 times 6.4. And I get 371.2. I'll go to 3 sig figs for my answer, 371 joules, but I'll keep that complete answer because I think I might need that later. Really what that means, Colin, is this object gained 371.2 joules of energy. What form? I think kinetic. I think as you're pushing this object, since it's accelerating, what can you tell me is happening to its speed? I think if you're pushing it, I think it's speeding up. I think it gained kinetic energy. Okay? Jordan, what's B want me to find? Well, I guess that might be force of friction times distance. Jordan, did they give me a distance in this question? Okay, so I'm going to lean on this method. Did they tell me friction? Not exactly. You know what? Let's go back to our free body diagram. We would say friction is what times what? So I'm going to write mu times the normal force times distance. I don't know the normal force. Oh, you know what? Get the obvious one. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. I think here, because we're nice level ground, I can go mu mg times d. Do I have all of those? Did they give me the mass? Check. Did they give me g? I know that. They gave me the distance. Did they tell me what's mu? I don't know. What's mu with you? Yeah, they told me what's mu. So 0.35 times 12.5 times 9.8 times 6.4. How much work was done by friction? You get 274.4. And this is wrong. For a candy, can anybody tell me why this is technically wrong? What? No, it's work. It's joules. I don't care. It's work. It's joules. It's the work done by the force of friction. If I had written the force of friction would be in newtons, but I wanted the work done by the force of friction. The work done by the force of friction is in joules. Good thought, but no. Yeah.
That should really be heat?
No. It is heat. But everybody point with your right hand this way, that way for you guys. Point your right hand out. Okay? That's which way in my picture the object is moving. Yes? Which way is friction pointing? Are they in the same direction? Are they in opposite directions? We looked at that. What should I do here? Negative. Because when you said heat, you're on the right track. We lost that much energy. Even though we did 371 joules worth of work, 274 joules went into heating up the floor, not speeding up the object. Friction and the distance are in opposite directions. Friction did negative work. Friction removed energy from the object. Really, it should say how much work was done on the object by friction, and the answer is, friction bled energy off. Yes.
But can you really have negative flow?
Yeah, you lose energy. Yep.
Are they losing?
Ready? Hold that thought. Because what does C want me to find? So, whoever was pushing did 371.2 joules of work. But what did we lose to friction? That much. The net amount of work, the amount of energy, Jake, that was left over that went into just having this block speed up, not heat up the floor, but speed up, is whatever that is. You had 96.8 joules. That, Leonard, went into making this block go faster. That went into kinetic. Everything else was wasted. Well, everything else went into heat. So total amount of work done, 371.2. That's whoever was pushing, or whether it was a machine, or I'll just make it a person pushing. That person lost 371.2 joules. They gave 371.2 joules to this block. Unfortunately, friction pulled out 274 joules. How could I say pulled out? Negative. Leaving 96.8. So D now says, assuming the object started from rest, what will the final speed of the object be? What's this question want me to find? Speed. Huh? What did we just find in part C? Work. You know what? The work energy theorem. It's putting everything together here. Another way to think about work, Jake, is to realize it's the change in potential plus the change in kinetic energy. I think I can do that, Jake. This question doesn't suggest there's a hill or anything like that, does it? Okay. And what's change in anything? Part D says, assuming the object started from. So what does that mean? I think my initial kinetic was 0. So here's what else I'm saying. This was my argument. I'm saying that extra 96.8 joules left over, that got turned in, didn't vanish, that got turned into kinetic. It made the block speed up. By how much? I don't know. Let's find out. We're going to get work equals a half mv final squared. How would I get the v final by itself? The work is going to stay where it is. I think it's going to be times by 2, yes? And divide by m. Mass doesn't cancel here because a bigger object would not be moving as fast, and a smaller object would probably be moving way faster. And then how to get rid of a squared? I think we're going to get the net work done. Oh, sorry, the v final is going to be the square root of 2 times 96.8 divided by, did I give you the mass? Oh, I did somewhere up there. Please tell me I gave you the mass somewhere up, 12.5. Square root answer. This object is going at 3.94 meters per second. If you keep pushing, then, Justin, you'll still be doing work on the object, although you're still losing a bigger chunk to friction as well. But if you keep pushing, this object will speed up, which I guess makes sense, because if you're pushing on an object, you're accelerating an object. Doesn't acceleration mean your speed has to be changing? Coming full circle to our definition of acceleration. Turn the page. Leonard's yawning. Good yawn. Tamara, what's part E here want me to find? Calculate the... Wait a minute, Duick. We just did that. Using what? Kinematics. So I'm not going to walk you through this, but you could have got the same answer by going like this. Find A using winner minus loser equals MA, divide by M. Who's winning? The applied. Who's losing? Friction. And then you could go VI equals 0, D equals 6.5, 6.4, Mr. Duick. A equals that answer, and you could find V final by going VF squared equals VI squared plus 2AD. And you would notice along the way, Rob, that you were actually typing a lot of the same numbers, a lot of the same calculations as we did here, just in a slightly different order with different steps. Which is the best way? You know what? I'd probably do it using method E, but I wanted to show you that our laws of the universe, Tice, still have to work. I have to be able to use two valid approaches, and I better be able to get the same answer. Example 6. Little thought experiment here. Oh, we get to vote. We haven't voted for a while. 3 projectiles, A, B, and C, are fired from the same machine on the moon. Why on the moon? I don't want to have air resistance. Okay, so you can pretend if you want from the Earth with no air resistance, or on the moon, which actually has no air resistance. With the same initial velocity, we should underline this. Their paths are labeled A, B, and C. At the points marked 1, which projectile will have the greatest kinetic energy? A, B, C, or all 3 will be equal? You know what? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So at the points marked 1, which projectile will have the greatest kinetic energy? A, B, C, or, hey, they all had the same initial velocity. It's all going to be the same. Who says A? Who says B? Who says C? Who says D? Well, the third answer. We've got about a 50-50 split. Convince me. What did you pick?
I think C.
C? Convince me.
Because you have the same initial velocity, but on the peak of
Mhm.
the hill, A and B has more potential energy, so C has to have more kinetic.
So he went to the law of conservation of energy. He said, look, if you go higher, that's more potential. That must mean, by definition, you have less kinetic. Is that okay? I actually thought of it in terms of projectiles. I actually just said, you know what? Kinetic energy is a half mv squared. I said each of those has a horizontal and a vertical component of speed. But I said, wait a minute, at the top, what's your vertical component of speed? What was your vertical component at the top always? How fast are you going at the top vertically always? 0. So I said, you know what? Really, this is just saying which one would have the biggest horizontal speed? C, because it got launched at an angle, lower angle. Slanty more. So you can also answer from kinematics. Yours was better. I never even thought of that. I like that. That was a good answer. Okay. So let's start thinking about types of energy. At the 3 points marked part 1, which projectile will have the greatest total energy? The greatest total energy. A, B, C, or all three will be equal. Who says A? Who says B? Who says C? 2? Who says D? Convince me. Convince me. Cade, convince me. Did you pick that one? Convince me. Don't write this down. Because what was their initial source of energy? What was their initial type of energy? Are they starting on the ground? Yes. So what was their initial potential? Energy. 0. Did they start with the same speed? So did they have the same kinetic energy? And that's the total energy. Energy can't vanish. Energy is not, they have the same total energy everywhere on their path. As they get higher, their potential increases, so which type of energy gets smaller? Kinetic, they slow down. As they go down, their potential energy decreases, so which type of energy gets bigger? Kinetic, they speed up. So how are we going to write this? The law of conservation of energy says that total energy remains the same everywhere on the path. And because all three started with the same amount, they'll have the same amount everywhere. But it turns out, Quinn, you can control the height by your angle. And that's what we were looking at in Unit 1. We were doing projectiles at angles, but you can also now think about it as an energy transformation. Oh, you want more potential? Give it less sideways kinetic. Make most of the kinetic vertical, and most of that vertical can, and I know it's a scalar, it doesn't have direction, but point it straight up, it'll go higher at the expense of not traveling as far. And okay. C. At the points marked 2, which projectile will have the greatest total energy? So part 2 is right there, and right there. This is just before impact, not after they've come to a stop. Which projectile will have the greatest total energy? Who says A? Who says B? Who says C? Who says it's all the same? Why? Copy. Paste. Right? Nice yawn. How many more am I doing? Tarzan. I've got a couple of videos to show you. It'll be a bit of a long lesson, but it is what it is. 3,000 Newton car at rest. I'd probably underline the word at rest. That's important. At the top of an incline 3 meters high and 30 meters long is released and rolls down the hill. What is its speed at the bottom of the incline if the average friction force is 200 newtons? Put your pencils down. Pause the video. We're going to pause here. I really want to get the test in before Christmas, so I'm probably going to have to do 2 lessons in one day. Your homework is, most of you haven't finished the lesson 1 homework. You need to finish that. If you have questions you can already do right now, I think is, I'm going to assign all of these, but for now you can do number 3. For now you can do number 4. For now you can do number 5. I'll give you those 3 for now. I'm hoping to do my test not next week, but the week after, so the week before Christmas. If you know you're going to be away, let me know. You probably want to write it before you go rather than after you go.